All right, spectroscopy is a process of using light to probe molecules. They're going to interact with light. That's going to be the handle that enables us to see what's going on. And so light is, of course, synonymous with electromagnetic radiation. And if we're talking about visible light, we're in the ranges, say, of 400 to 700 nanometers. And this sort of UV range would be shorter wavelengths. The infrared would be longer wavelengths. And then there are other regions outside that aren't necessarily relevant to what we want to talk about today. So light contains both an electric and magnetic field, and they sort of occur in 90 degrees from each other, as shown here. And the electric field can interact with electrons, and so that's useful to us because the molecules that we study certainly have electrons. Light is it's cheap. Now, the instrument that utilizes it might not be, but it itself, of course, is a rather renewable resource. It's fast in the sense that we can utilize it, and it doesn't take a lot of time for a molecule to absorb a photon. It's also safe for the most part. There, of course, are dangers of UV and X-rays and things like that, but compared to some other techniques, it's quite safe. And the speed of any wave is given by the product of the wavelength and frequency. In the case of light, the speed is going to be the letter c, which is a specific speed, and the wavelength, given typically in nanometers, as we know, is lambda, and the frequency, given in inverse seconds or the unit hertz, we might be familiar with that, is nu. That's not v, it's nu, the Greek letter. Now we can take that basic equation and also the equation for the energy of a photon shown here. Specifically, the energy is equal to Planck's constant times the frequency nu. And we can plug in the speed equation, and we end up with this expression right here. Hc over lambda is the energy of a photon. And what that tells us then is that higher energies of a photon are associated with shorter wavelength, and that should make sense here. If you think about if we shrink the wavelength of a particular photon, it's going to increase the frequency. That's going to therefore increase the energy. So I'm going to talk about the absorption of light of electromagnetic radiation, and here we're just looking at a simple hydrogen atom, like the Bohr model, but these principles will be true for other things as well, certainly molecules that we'll be studying. So electrons exist in different electronic energy levels, or N, and moving between them is known as a transition. Whenever that happens, electromagnetic radiation is absorbed or emitted, and the lowest state is called the ground state. So let's say we have an electron here in the ground state, and these n equal 2 and n equal 3 then are excited states, and we can promote that electron to an excited state by shining light upon it. And so if we have a photon of the appropriate energy, it will cause that electron to move up to an excited electronic state. And so what matters for us is that molecules absorb photons whose energy matches the gap between the ground and excited states. And so this particular example, there is an energy difference between n equals 1 and n equals 2, and the only photon that can cause the transition, the excitation of this electron, is a photon whose energy matches that difference. If we wanted to promote this electron up to n equals 3, we would have to have a photon of the energy that matches that greater gap there, that higher energy photon in that case. Conversely, if we relax an electron from n equals 2 or n equals 3 down to n equals 2, down to n equals 1, that will result in the emission of down to n equals 1, that will result in the emission of a photon. And so for us, we're going to spend much more time worrying about absorption and not as much about emission, but we will see a couple examples of that. So energy level diagrams are shown here. These are also called Jablonski diagrams. These help us understand some of these basic phenomena. And what we're looking at here is, let's look at the first panel. Notice we have these different electronic energy levels, right? So this says E0, but it's kind of like saying N equals 1, N equals 2, N equals 3. And so those are the electronic states. But notice that these different levels within each one, those are vibrational energy levels. So we have electronic energy levels, and within those, vibrational energy levels. And if we want molecules absorb photons whose energy matches, right, the difference between these states. And so if we're absorbing in the infrared region, those are long wavelengths or small energies. And so really we're just looking at changes of molecular vibrations, and that should make sense if you remember a little bit about what infrared spectroscopy does. But we're going to spend more time thinking about these sorts of transitions, where we're actually going from one electronic state to the other. In one case, it could be visible absorption, so we're absorbing photons whose wavelengths are in the visible range. And notice that we're demonstrating here that's only a transition between adjacent electronic energy levels. But UV is higher energy, shorter wavelength. Means then that we're going to transition between energy levels that are further apart. So that's absorption, and we'll explore that in quite a bit of detail. Once those electrons are excited in excited states, then they can sort of relax back down to the ground state through non-radiative means, and this is essentially that energy is being lost to heat. That's one possibility. The other possibility, and which is more similar to what I showed on the previous page, is something like fluorescence, where the energy is then re-emitted as photons. Now, one thing to point out is the vibrational energy levels decay very, very rapidly back to the vibrational ground state. And so in fluorescence, that's always going to be the case, that the excited electrons are going to start off at some excited vibrational state, but very rapidly decay to the ground vibrational state within an excited electronic level. Then when that photon is emitted, equivalent to the energy here, then it'll relax to the lower electronic state down here. So I want to talk about some example molecules and what their absorption spectra would look like. So this one right here is an isoprene unit, and we're looking at the absorbance, and we'll define that a little more carefully in a little bit here, as a function of wavelength. And so we're asking, so where is this molecule absorbing at the most? And it has a lambda max, as we would say, and that is the wavelength at which this molecule absorbs the most photons. It's about 222 nanometers for this particular example. And so we'll be looking at some absorption spectra in class. No, we won't. But let's look at absorption properties of other compounds, ones that are particularly relevant to biochemistry. And notice we got the scale of the spectrum going vertically here, going 200 down to 600 nanometers, I should say up to 600 nanometers. And that is, most biologically relevant molecules, are going to exist somewhere in that range. So we're looking at UV down at the low end here. So UV, we're kind of in the 200, somewhere around 350 nanometer range for that. The thing about UV is it's not always super safe, right? So you can't shine it on your face, can't shine it in your eyes, so there is some precautions that have to be taken when we're talking about UV, and most of the time it's the instrument takes care of those issues. Another downside to UV is that it requires quartz cuvettes. And so plastic and glass and things like that absorb UV wavelengths. And so if we're doing anything with UV, we have to have the appropriate cuvettes. There are some plastic ones that can go down to the near UV, but they're not perfect. But the upside is that there are many molecules here There are lots of molecules that absorb in the UV, kind of examples of which are shown here. So the peptide bond, of course, which is present in all proteins, absorbs in the 220 nanometer range. And so if you put a protein sample in a UV visible spectrophotometer, you're going to see a very large peak at 220 nanometers. Nucleotides, we're talking about DNA and RNA. These are going to absorb kind of in the 260 nanometer range. It's somewhere less, some are less than that, some are a little bit more than that, depending on which particular base we're talking about, but in that range. And then there are the aromatic amino acids, which again are going to be present in protein samples. So we've got phenylalanine, we've got tyrosine, we've got tryptophan. These are all typically going to absorb somewhere around 280 nanometers. And as we'll see, 280 and 260, these are the numbers that we use quite a bit in the biochemistry laboratory because they help us understand what's going on with protein and nucleic acid as well. So from there, we're going to transition into the visible range. And this is kind of more in the 350, 400 range, up to 600 nanometers is kind of where those molecules are going to be. This is, of course, safe. It's just visible light. And the cuvettes we can use would be glass and even plastic. And so those are very cheap and easy to get. Quartz cuvettes are expensive. But the downside to visible studies is that there are actually fewer molecules that absorb in the visible range. Fortunately for us, our molecule that we're going to study in this class does absorb in the visible range, so we're in luck there. But examples would be things like flavins. The flavin cofactor part has conjugation, keratines and heme, right? These things, as we're going down this chart, we're seeing more and more conjugation, and that's going to lead to longer wavelengths that these things are going to absorb. If you folks took physical chemistry or will take physical chemistry, you'll appreciate that a little bit more, but we're not going to go into too many details about that here. So let's talk about quantifying this absorption. How do we do that? And so this is roughly the sort of a layout of a simple spectrophotometer. I will show a little bit more detail here in a minute. But what happens is we have a light source of some kind. It goes through a monochromator, which, as the name implies, right, one color, meaning it's going to act as a prism and separate out the spectrum, and so we can get a single wavelength, plus or minus some error there, of light shining through our sample. And so we can call that light I0 because it has some intensity, and 0 meaning sort of the initial intensity. It's going to shine through our sample, which is going to have a certain width, right? There's a certain distance here that the sample is in this particular cuvette. And sometimes we call that B, or sometimes L is the length, the path length. And the amount of light coming out of the sample is going to be I with no 0. And so that means like some light has been absorbed. The molecules have absorbed some of that light. And so how do we quantify that? We have the transmittance, which is literally just the ratio of I over I0. And sometimes you multiply that by 100 to get the percent, right? So it's the that's the transmittance. Now the issue there is it decays logarithmically with increasing length. So if we're going to plot that transmittance value as a function of concentration or the path length, right, basically how many molecules is that light going to encounter, that is not linear. It has a sort of logarithmic kind of decay like that. And that actually is kind of difficult to deal with in a laboratory. And so absorbance is way more common. And this is just, absorbance is the negative log of the transmittance from above there. And this now increases linearly with increasing concentration. So if we look at absorbance, capital A, sometimes I'll write ABS as a function of concentration, this will be a straight line, and that is way better. You can plot things like that in Excel. You can get equations in Excel. Dealing with curves is a little more complicated and doesn't work quite as well. And so absorbance then lets us use this thing called Beer's law, which hopefully you're somewhat familiar with, which is that the absorbance of a sample equals some extinction coefficient epsilon times the path length L or B, depending on who's writing the equation, times the concentration of the sample. And so we can use Beer's law if we know, say, what the extinction coefficient is for a molecule. If we know the path length, guess what? It's almost always going to be 1 centimeter. And we measure the absorbance, we can solve for C and determine the concentration of a sample. Now, there are some limits to absorbance and to these instrumentation. And the issue is that we want the absorbance reading to be, say, less than 1.0 in general. And we can go a little bit more detail than that. I mean, some instruments can do well above that, but it's a general rule of thumb that we want to keep the absorbance values maybe more in the range. If you want to be safe, maybe we want to be somewhere between 0.1 and 0.9. So there might be exceptions to those rules. If you start getting too low of a concentration, too low of an absorbance value rather, then the instrument may or may not be able to read that very precisely. Kind of depends on the instrument. So it's safe bet to be somewhere in this range. And if you're way higher than that, your sample needs to be diluted. If you're lower than that, then you can't necessarily concentrate your sample always, but you got to think about what's happening with your setup that you have such a low absorbance value. So let's talk about that extinction coefficient and what it means and maybe some examples of what those would be. So the molar extinction coefficient, epsilon, it can be other things. Sometimes there are mass extinction coefficients. We're talking about the molar extinction coefficient. This indicates how strongly a specific substance absorbs light at a given wavelength. So we've already have two things in there. It's a specific substance. So every different molecule, whether it's DNA or RNA or Centa, a molecule you're going to get to know, is going to have a particular extinction coefficient, and it's at a given wavelength, usually the lambda max, that wavelength where the absorbance is maximum. So beyond that, though, it can vary with pH subtly, it can vary with the solvent, and it can vary with temperature. And so it's important when we're setting up experiments that we control for all of these things. pH controlled by buffers. Temperature, make sure we're not measuring it at 95 degrees C versus 20 degrees C. So these things definitely matter. And certainly the first part of our course, Unit 1, we're going to spend a lot of time working with protein. And as I mentioned, we analyze protein at 280 nanometers because of these aromatic side chains. And so, for example, tryptophan has an extinction coefficient at 280, so a lot of times we write it like that, of kind of close to 6,000. And here are the units: inverse molar, inverse centimeter. So inverse molar, inverse centimeter. Now, why does that make sense? That's a weird set of units. And to answer that, let's look back at this page and think about Beer's law. Absorbance is a negative log of transmittance. And transmittance is just a ratio of sort of a photon count. So absorbance has no units, right? So the left side has no units, and now the right side of this equation also must have no units. So the path length L is in centimeters, and concentration is in molar. So to get no units, we have to cancel those two out, and then epsilon, therefore, needs to be inverse molar, inverse centimeters. So that's why those units seem a little funny there. The good news is that the path length is almost always 1 centimeter. And I don't want to say always, but almost always, and always in our class, the path length will be 1 centimeter. And so the centimeters of this kind of disappear, and we don't have to worry about measuring that path length ever. Now, another amino acid, tyrosine, its extinction coefficient at 280 is about 1,200 per molar per centimeter. So, not as intense. And so it means that tryptophans really are the major source of absorbance in protein, and tyrosines are less so. Now, DNA samples are analyzed at 260 nanometers. Double-stranded DNA, for example, if we had one absorbance unit, that would correspond to a sample of double-stranded DNA that is the concentration of 50 micrograms per milliliter. Now, single-stranded DNA actually absorbs light more strongly, and so one absorbance unit of single-stranded DNA indicates that the solution is 37 micrograms per milliliter. So we will talk more about DNA later on in this course. We're going to concentrate a little bit more on protein in the first half. I want to talk a little bit about the instrumentation and sort of the layout. I'm showing two different types here. The first one is called a single beam spectrophotometer. And it'll have a light source of some sort, whether it's UV or visible. It's going to have a monochromator, right, which is going to select the wavelength, the particular wavelength we want. And then we have our sample, and finally a light detector. And a light detector can be several different things. It could be something called a photomultiplier tube. It could be a diode array. Or it could be a charge-coupled device. This isn't an instruments class, but just be aware there are a few different ways that these instruments can detect the light. So that's a single beam. If we want to run an experiment in a single beam spectrophotometer, we have to put a blank in and blank the instrument, and then take the blank out, and then put our sample we want to measure in. But a dual beam, shown here, always has a reference cell. So this is reference or blank, however you want to consider it. And then our sample is put here. And so it kind of splits the light, and it always has a blank or a reference that it can look at. For us, we're going to always be looking at single beam instruments for the experiments that we are doing. And you'll be using these two instruments in class. One's called an Agilent Carry 60. Some of you might get to use the 100. Same basic instrument, just a little bit extra features. So the Agilent Carry is it can do both UV and visible wavelengths. It's very high precision, very expensive instrument. And so we'll use this for some experiments, but we don't have enough of these. They're too expensive for every partner to have one for themselves. And so instead, we're going to use the Vernier SpectroVis. These devices here, maybe you've used them in other courses. These have some limitations in that they really only look at visible wavelengths and barely some near UV. Their precision is modest, and the cost is modest as well.